Hey everybody, and welcome to Chapter 7. So we are starting a new chapter, and I feel like I say this almost every chapter, but this is a big important chapter. And I do remember saying earlier in the semester that there are a couple of chapters that are really big game changers, and one of them that I talked about was Chapter 4, because that's where we introduced z-scores. And z-scores, as you've seen, do not go away. They are something that we deal with for the rest of the semester, basically. Similarly, I think that Chapter 7 is also maybe one of the most important chapters as well. I think 4 and 7 are maybe the most important chapters all semester, because the ideas that we're going to be talking about in this chapter are going to recur. They're going to happen over and over and over again. So I may go a little bit slower in some cases. And again, if you have any questions, or if you're following along in the video and you're not quite sure how exactly I got the conclusion that I got, feel free to email me, and I'd be very happy to talk about it with you. Because I know that, just watching a video is helpful, but not always, enough. Alright, here we go. So let's talk about hypothesis testing. So at the beginning of the semester, we talked about the difference between descriptive stats and inferential stats. And so this unit, chapters 5, 6, and 7, have really been kind of like transitioning us out of descriptive stats and into inferential stats. One thing that we are going to see all the time as psychologists and as therapists and as counselors is trying to understand whether or not our patients are any different than the quote-unquote normal population, however you want to define that term, whatever. But we want to know whether or not our patients are different than other folks in society. That is something that you're going to be dealing with all the time, and you're going to use stats to help show that and to help answer that question. So, for example, are you sure that your therapy technique is actually effective? Are you sure that the patients, maybe you think that the patients that you're getting this year are more depressed on average than in previous years? You can test those kinds of things using what we're going to be talking about in this video. So there's a systematic way to do it, and that's what we're going to be looking at. So why is this an important chapter? Because this idea of hypothesis testing is going to be crucial for every single chapter from here on out. Every single chapter from here on out, we're going to be testing something. We're going to create hypotheses so that we can test them and that we can analyze them. And yeah, so let's get into it. Alright, so we're going to be looking at that. We're going to be talking about p-values as well. P-values are very complicated, and again, one of those things that don't go away. So let's get into it. This video is going to be split into a couple of different pieces. So this first bit is going to be kind of about what hypothesis testing is. I'm going to give you a quick kind of example. And the second video is going to be how to find the z-critical value and how to apply the math to do hypothesis testing. So if you're scanning through this video trying to figure out what stuff is where, this is going to be the kind of conceptual video. The next video is going to be more applied, like how to calculate those things, and then I'll create a third video kind of walking you through how to solve one of these from scratch. So let's get into it. I've spent enough time setting this up. Let's get into the juicy details. So why do we need stats? Because we are a science, and every single science uses stats. So this isn't just, for psychologists. Even though this class is titled Statistics for Psychologists, we're talking about the same stuff that biologists talk about. Biology has its own stats class that's a requirement for the major. So does most sciences, I guess. But I guess the thing that came to mind is econ, economics has it, sociology has it, the GPS major has it, communications has a stats program. A lot of different fields have stats, because we all, anytime you're doing science, you have to rely on stats to try to show whether or not your groups or conditions have any effect or are different in any way. So the examples that I'm going to be giving are largely kind of behaviorally focused, but you could replace these examples with amoeba or with parameciums or with neutrinos or whatever you want, because every science is going to have the same kind of statistics governing that stuff. Now, the reason why I'm belaboring that point is because at the very beginning of the semester, I talked about how, like, stats is really about being able to speak the language and understand the language. This is one of those really crucial chapters that's going to help us understand the language. We're going to be speaking the language. We're going to be doing stats a lot throughout the semester, but this is where we're really going to talk about some of the abstract principles behind what we're doing. So we would be interested in learning about how behavior affects individuals and groups, and we need to know that, so that's why we need stats to do that. So for example, let's say that we develop a treatment for anxiety. We're going to give that to 10 patients. If we find that 7 of them seem to show signs of improvement, does that mean our treatment works, or does that mean it is random chance? So it can be very tempting. You give 10 people, a treatment, and 7 of them seem to show signs of improvement. That feels like a win, right? But if we want to define random chance as 50%, then that means that we could expect that 5 of them are going to show signs of improvement just by chance, which means that 7 is actually only 2 better than chance. Does that mean it's effective, or does that mean that this is just random variability and random variation in behavior that makes it look like it actually works? Another example, if we want to kind of go back to politics, in Chapter 6, we use a lot of examples with politicians. So let's say in recent pollings, most voters prefer politician A over politician B. How do we know for certain what's going to happen on election day? These are things that we can answer using stats. One final example, if we sample 1,000 participants, we find that introverts seem to make more money a year than extroverts do. Does this mean that personality trait is going to increase your income, or is it just random chance that this happened? That based on our sample, that this was just kind of an aberration, just an anomaly that that they had more. This is why we need stats, to help us understand, to find the message, to find the story in all of this variability and all of this variation. So to get there, let's talk about audiophilia. So some of you may know that I really love music, and so this was the first example that popped into my head was in my sensation and perception class. One of my favorite things that we do is there's 1 week where we test how well can you pick up on the quality of an audio stream. So for people that love music, this can be a very contentious subject because, as you have CDs, you have Spotify and Apple Music, but you also have vinyl records, you also have cassettes, there's lots of different ways that you can approach listening to music. They're not all the same. That, whenever you stream something on YouTube, that quality is much lower than what you would experience in Spotify, and both of those are much lower than what you would experience if you had vinyl. But the thing is, most people can't really tell the difference, right? For some of you, it may be news that YouTube has really, really bad audio quality, and so if you've been listening to music on YouTube, usually the audio quality is just not very good. So somebody who's an audiophile, who loves music and loves thinking about the quality of music, they would say that's kind of bad. They might prefer vinyl. So in this case, my friend claims to be an audiophile, and she says that she can tell the difference in audio quality when she's listening to vinyl records, which are the highest quality, versus a YouTube stream, which is much poorer quality. And I don't believe her. I'm like, you know what? I think this is a placebo effect. I think that you can't actually tell the difference. And so she says, okay, well, design a test and I can prove it. And I take her up on that, so I'm going to give her 20 tries. I'm going to blindfold her, and I'm going to make her listen to 20 separate songs, and I'm going to sometimes let her listen to the YouTube stream, sometimes let her listen to vinyl. And then the question is, will she be able to notice the difference? So I do that, and she's able to tell, out of those 20 times, 15 times are correct. So 15 out of 20 times she was correct in choosing the vinyl recording. So, again, does that mean that she is actually an audiophile and can tell these really small differences in the audio stream? Or did she get lucky? Because if this is, if it's 50% chance, then that means that we can expect that she would get 10 out of 20 correct just by chance. So is 5 more really a big deal? That's where stats comes into play. So statistics is going to tell us whether or not this was just luck and random, guessing, or whether or not she actually is an audiophile. All right, so is 15 out of 20 a big deal? So if we're making any kind of claims, we have to think about the baseline rate. We have to think about what we expect based on chance. I already told you that's going to be about 10, right? 10 would be, lucky guesses if you were just guessing. So if she got 15 and she is actually guessing, then she did get quite lucky. That's our job to figure this out. I'm not going to go over the details necessarily of how to figure out the probability of getting 15 guesses correct out of 20. It is a binomial test that you would need to do, a binomial analysis, something that we're not going to talk about this semester, because you're not really going to see it all that much. But the probability of getting 15 guesses correct out of 20 when you're just guessing is pretty low. It's basically less than 2% chance. It's not likely at all that that she was able to do this. So if I crunch those numbers and I find that the probability is that there's a less than 2% likelihood that she got this just by guessing, then I am going to say, you know what, you must be right, because that's very, very unlikely that you were guessing. Because to get 15 correct guesses, that's you must have a lucky rabbit's foot or something. So we know that 15 out of 20 does seem to be a big deal, because it's very unusual, very unlikely for somebody to get that just from guessing. But what about 11 out of 20? So if she challenges me to do it, and I get 11 correct out of 20, so is that good? I did do above chance, right? So if we know that chance is 50%, then that means that 10 out of 20 is chance. This looks like I did better than chance. But if I look at the numbers, the probability of me getting at least 11 correct is going to be about 75%. So what does that mean? Or I should say at most 11. But yeah, so the probability of getting 11 correct is going to be about 75%. So there's a pretty good chance that I could have just been guessing in this case, because guessing 11 out of 20 correct, so imagine if you had 11 true-false questions. Just by doing them randomly, you're going to get half of them correct if you don't know the answer to any of them. And you're just guessing without even looking. So to get 11 out of 20 of those is not so unusual. So I don't have enough evidence for me to say that I am an audiophile. To me, this is just not enough evidence to show that I'm doing more than just actually guessing. So this chapter is going to be all about how do we figure this out? How do we figure and look at random variability and chance and guessing versus actual group differences? Okay, so if we were to frame this in terms of testing, so thinking back to your research methods experiences, how do we form these as hypotheses? So the way that we're going to do this is, and this is really important for stats, because in every chapter from here on out, in most of them, we're going to be breaking this down into what is the hypothesis. Let's define our hypothesis before we even analyze any data. So in this test, there are two separate outcomes. There's hypothesis 1, which is that my friend cannot tell the difference between high quality and low quality audio. Hypothesis 2 is going to be that my friend can tell the difference between high quality and low quality audio. So we have these two competing hypotheses, and that's important. Every time we're analyzing something and trying to draw these kinds of inferences, there's going to be two hypotheses that are in direct competition with one another, and it's our job to figure out which of those seems most likely, which of those hypotheses seems most likely to be true. And every experiment is going to have at least two hypotheses, where one of them is going to be what's called the null hypothesis, one of them is going to be called the alternative hypothesis. Sometimes people call this the experimental hypothesis, sometimes people will call it the research hypothesis. Either way, it doesn't really matter. But the important thing is that we have a null and we have an alternative. So what does that mean? The null hypothesis is going to be the hypothesis that says this is just guessing, that there is no actual differences here, and that any differences that you do find are going to be because of chance or because of random variability. So if we look back at our hypotheses here, which of these is the null hypothesis? is going to be the first one, right? Because the first one is saying that she cannot tell the difference between high quality and low quality audio. That's going to be my null hypothesis, which basically means that there is no difference between these two. That we're going to say that that this is our assumption, and we need evidence to overturn the assumption. So as mean as it sounds, our job as scientists is to say that our friend is probably not right unless she can prove us wrong, because we need that evidence. And I know that seems unfair to our friends, but we have to have that evidence in order to overturn the hypothesis. So our null hypothesis is going to be that there is no difference, that there's no difference between in her ability to detect high quality and low quality audio. The alternative hypothesis, on the other hand, is going to be essentially that your friend can tell the difference, so that there will be some difference between her perception of high quality and low quality audio. And if that's true, then we can rule out the null hypothesis. So another way to think about this is that our job as researchers and as clinicians and therapists is to assume, we're going to assume the null hypothesis until we have enough evidence to overturn it. And then we can operate with the alternative hypothesis. So think about it like that. We're going to assume that there is no differences amongst our groups, amongst our conditions, unless we have the right data to prove us wrong. This is very, very different than how a lot of us normally approach this. A lot of us will kind of jump into this assuming that we're going to find differences, but we have to let the data speak for itself. We have to say we're going to assume there is no difference unless we have data to the contrary. So when we write this out, and this is going to be a little strange, but we're going to be writing this out in hypothesis syntax. So we're going to have the HO, this is the null hypothesis, the HO, and the HA, which is going to be the alternative hypothesis. Sometimes, including the book, can refer to this sometimes as HA, or it can refer to this as H1. That's fine too, because sometimes people will have H1, H2, and H0, which basically means they have a null hypothesis and two competing alternative hypotheses, and that's okay. In our case, this semester, we're mostly just going to have HA and HO. We're only usually going to have these two. So what we would say here is a null hypothesis would be something like HO is going to be equal to, or actually, let me back up for a second. HO would look something like this, where we have x bar 1 is going to be equal to x bar 2. In other words, my null hypothesis is that the mean performance on high audio quality is going to be the same as the mean performance on low audio quality. So the null hypothesis is always going to assume that these groups are the same in some way. Other versions of this could be that the null, in other words, that it is greater than or equal to or less than or equal to. And again, the key here is equal. So it's okay to have it. A null hypothesis always has equal somewhere in it. It may not be the equal sign necessarily. It could be, less than or equal to, or greater than or equal to, or just straight up equal to. Either way is fine. The alternative hypothesis is completely different, because the alternative hypothesis is going to look, and I'm going to write this over here, where we would say something like x bar 1 is not equal to x bar 2. Or, which basically just means that our friend's performance on that task is different. That she does detect a difference, but we don't know, is she detecting the high quality more or the low quality more? We don't know. But we can also express this as greater than or less than. So honestly, if we were wanting to be very specific about this previous example, our friend who claims that she can hear them more, if x bar 1 is going to be for high quality, then we would say that she is operating under this, the alternative hypothesis, that she is saying that she's going to get more right than not. All right, so. And this is just going to be very similar to what I was pointing out here. I was using X bar previously because that's usually an easy way to think about it. But most times we're actually going to be referring to mu. And so I kind of regret that now that I think about it. It would have been more helpful to start out with mu, because we're mostly going to be doing this as mu. But honestly, on on an exam, if you put X bar, I'll give you partial credit for it because they roughly mean the same thing. We're talking about means here, right? But the reason why we're using the population mean and not the sample mean is because for this hypothesis, we're using inferential stats. We are assuming it's going to generalize to the broad society, to the broad population. That's why we use mu here as a population, sorry, as a mean parameter and not X bar in most cases, because we're trying to talk about the population. So why are we using that here? Well, as I just mentioned, we're trying to extrapolate. So we're trying to make broad conclusions about our population. So other examples of this, to think back to some of those examples we looked at earlier. So politician A votes are going to be equal to the politician B votes. This would basically be that we don't anticipate a difference between the politician votes. Or if we said that we expect that introverts and extroverts make the same amount of money, we would express that as mu for introverts is the same as mu for extroverts. Then, if you had an alternative hypothesis, if you suspected, based on the data that you found, that there is a difference somewhere, then you can express that using an alternative hypothesis. The alternative hypothesis is going to be the assumption that your data is not going to come out due to chance. So then you can say that you suspect that one group is going to be greater than or less than the other group, or one condition is going to have higher values than the other condition. So in the previous example, what would that look like? If the alternative hypothesis here is that my friend is an audiophile, what would that be, right? Basically, we would just say that her responses are not going to be at a chance level. And that's actually going to look a little bit different, because what that means is, when we write this out, for the previous example, that the mu of our friend's responses are going to be equal to 50%, which in this case is going to be 10, right? Because we talked about how 10 is essentially kind of random chance. So that would be the null hypothesis, because we're not expecting her to be able to do that. So we expect her to do randomly. But if we were trying to say, well, what is the alternative? The alternative is going to be whatever is the opposite of the null, which is why it can sometimes be helpful to identify the alternative hypothesis or the null hypothesis first and then work backwards to figure out what the other one is. So in this case, we expect her to, for the null hypothesis, to not have any differences. So that means that our alternative hypothesis is going to be the opposite, that there is some difference. So then we would say that mu is not equal to 50%, or that mu is not equal to 10. And that's just our alternative. Afterwards, if we wanted to do a follow-up study, we can get more specific, where we could say that we think it's going to be, you know, in this case, less than or equal to 50, and this one is going to be greater than 50. But either way, you want to make sure that these two things are in opposition, that they are essentially opposites of one another. So if I gave you, for example, the null hypothesis is less than or equal to 50%, then without even looking at anything else, you already know that the alternative hypothesis is just the opposite. So what is the opposite? The opposite is going to be greater than 50%. If, and that's for the alternative hypothesis, if I gave you that your prediction for an alternative hypothesis is going to be that mu is less than 50%, then you would say that the null hypothesis is going to be greater than or equal to 50%. All right, so that's how we kind of define what these hypotheses are. This is one of those things that just takes practice. So, you know, along the way, try to guess what you think the hypotheses are going to be for the null and for the alternative. Check out the book for other examples of that. Check out online for other examples, because again, this is one of those things where just practice makes perfect whenever you're trying to figure this stuff out. All right, if you have something like this, where it's not equal to or equal to, that's called a bidirectional hypothesis, which means you don't have a prediction either way. If you do have a prediction either way, then we're going to call that unidirectional. In most cases, we're going to focus on bidirectional hypotheses. There's a good reason for that, which we'll talk about later this semester, but it's honestly because it's a more conservative test. In other words, you're less likely to make errors if you go with a bidirectional hypothesis. It's more conservative. It's more likely that you're going to not make false claims whenever you use bidirectional hypotheses. Now let's talk a little bit about the alpha level. So we haven't really talked about alpha level at this point in the semester. So what is the alpha level? Alpha level is a way of talking about how likely are your results to come from chance. So the alpha level is going to be our threshold. It is expressed like this, like a lowercase a for the Greek alphabet. So if you see this little guy, that is your alpha level. In most cases, we're going to say that alpha is going to be equal to 0.05. Sometimes you're going to see alpha is going to be equal to 0.01. Either way, it's always going to be less than 1. The alpha value can never be greater than 1. So generally speaking, the industry standard is that alpha is 0.05. In other words, we are going to use this alpha as a threshold. Anytime we have a probability that is less than this threshold, we're going to say we reject the null hypothesis because this is very, very unlikely. It's less than 5% likely to occur by chance. So thinking back to our previous example where our friend was doing that, that audiophile test, we found that, that she had less than 2% likely to have it done by chance, which means that 2% falls less than this 5%, the 0.05, which is 5%, which means that we would reject the null hypothesis. So your ability to reject the null hypothesis depends on whether or not the probability you find using, in most cases here, the z-score calculator that I showed you previously, that if that probability is less than 5%, then you can reject the null hypothesis. So, can we reject the null hypothesis for her results? Yes, because we found that it is less than 5% likely. But what about my results? Remember, my results were like 78%. We can't reject the null hypothesis there. We don't have enough data, we don't have enough good evidence to show that I am an audiophile and I can pick out these high quality streams. We don't have enough evidence. So we would just say that we cannot reject the null hypothesis. So for her, we can reject it. For me, we cannot reject it. This is going to bring us into, and you may remember I keep emphasizing how great it is to draw out your normal distributions, so that way you can kind of see, where your z-scores are. This is part of why that's so important, because when we're doing hypothesis testing, we're looking at that 5%, right? And the 5% is almost always going to be way over here in the tails, and maybe in the negative tails or in the positive tails. That these are the really unlikely outcomes. And so if you find that your z-scores are landing out here in the tails, that means you're going to be more likely to reject the null hypothesis. If you find that your z-scores falling in here in the bigger parts of the distribution, you're probably safe. You're probably not going to be able to reject those null hypotheses. So this stuff over here, what they call the shaded region, that is going to be the key that we're looking for. Is it less than 5% likely? And if it is, then we're going to reject the null. All right. And this is the last slide I'm going to talk about before I take a break and do a second video to talk about where we find those probabilities. So here's ultimately what we want to know when we are doing a hypothesis test. We are going to be looking at what we got in our data. That's going to be X bar. So the sample mean, that's what we got in our sample collection. We're going to look at what we expected to find. We have to have our mean for the population to do that. And then we're going to look at the random variability in our data, and that's going to be the standard error. So, in other words, what we're saying, what we are trying to test is what did we get, what did we expect, and how does that compare when we factor in the random variability here? So thinking about this in terms of the previous example, what did we expect? That's going to be what we expect if there was just random chance. For us, that's going to be 10, right? For our friend, that was a 15, right? Because she actually got 15. And what was the random error? I didn't provide you with that, right? So that's okay. We can't actually calculate that for here, unless I said, hey, assume the random error is 2 or 1 or whatever. Then you could calculate that to try to find that. So in the next video, we're going to be talking about the difference between z-scores, because we're going to have a z-obtained score and a z-critical score. They sound kind of similar. They're actually quite different. We'll talk about those differences and how to calculate them in the next video. Thanks so much for following along, and I will see you in video number 2.